So the third model we're going to look at is molecular orbital theory, sometimes abbreviated MO. This calculates orbitals for the entire molecule instead of just looking at individual atoms. Even for a simple molecule like H2, we can't solve the Schrödinger equation exactly. It's impossible. So to do this, they use trial functions, basically an educated guess. It's like, well, let's try this. And you stick that into the computer, and the computer says, not quite. And so you say, well, let's move it this way, and the computer says, okay, you're getting closer. And it's playing warmer, colder with the computer until you get something with the lowest energy. So all of that's very, very complicated, and we're not going to do that. What we're trying to do with these big computer simulations is we're trying to figure out what nature is doing, but we're never as good as nature. Nature is always better at minimizing the energy of the orbitals than we are. But that's the idea. So we can look at what's called a linear combination of atomic orbitals. So it's a weighted linear sum of the valence atomic orbitals of all the atoms in the molecule. So instead of taking the orbitals on one atom and messing around with those, we're taking all of the orbitals, all the valence orbitals for all the atoms in the molecule, and kind of hybridizing those. So this linear combination is the simplest trial function that works reasonably well. What we end up with for these linear combinations are orbitals that are often hybridized over the entire molecule. Not hybridized, delocalized. They're delocalized. So this orbital now, instead of just being between two atoms, like the hybrid orbitals are, it goes all over the molecule. Oh my goodness. Okay, so let's look at hydrogen, H2. So hydrogen has two orbitals, right? Let's start that over again. Each hydrogen has one orbital, an s orbital, and it's got one electron in there. So here's an s orbital from the one hydrogen, s orbital from the other hydrogen. So when we linearly combine these, we get a bonding orbital that's lower in energy. It's got this sort of a pill-shaped, and that's a bonding orbital. And this is called a sigma orbital because of its shape. If you look at the end and you look down the barrel, it's like looking down the length of a hot dog, right? It's spherical, circular. The energy of this orbital is going to be lower than the atomic orbitals it was formed from. And so we call this one sigma 1s. Sigma because of its shape, 1s because it's combining 1s orbitals. Yeah?
All diatomic elements do similar things like that?
Yes. All diatomic elements do similar things. They form molecules like this. And this molecular orbital theory is the most advanced, the best model of bonding. And so actually all molecules are going to do these molecular orbitals. The good thing is that valence bond theory explains most of what we need to know without getting into this crazy molecular orbital theory. But there are a couple of reasons that we need to have an idea of what molecular orbital theory is. And so we're going to go over just the very basics of it so that we can say, and this is why this other thing happened. Because we need to be able to justify that, even if we don't completely understand it. So we can combine those orbitals so that they are in phase, they reinforce each other. That gives us the bonding orbital. And then we can also overlap them or combine them so that they are out of phase. And so when we combine these out of phase, it's a bit like subtracting instead of adding. And we get a different shape. We get something that looks like this. there's a big node in the middle and two things on the side. This is an anti-bonding orbital. This not only does not promote bonding, it fights against bonding because it takes the electron density away from between the two atoms. You think of this as destructive interference, so the waves are interacting in a destructive way. This orbital is higher in energy. It's still spherical if you look end on. So it's a sigma orbital. It's made from the 1s orbitals, and we put a star here because it's an anti-bonding. So we've got two atomic orbitals, two 1s orbitals. They can combine constructively, like adding, and they can combine destructively, like subtracting. And so we combine two orbitals and we get two orbitals. One is a bonding orbital with lower energy, and the other is an anti-bonding orbital with higher energy. So instead of trying to draw these weird pictures, we use a diagram. It's a little bit like a molecular, an orbital diagram. So as typical, we make energy increasing as we go up the page. So here's the orbital diagram for the hydrogen and for the other hydrogen. And then we're going to look at the middle of how those orbitals could combine. So if we combine these, adding them, we get a bonding orbital that's lower in energy. If we subtract, we get an anti-bonding orbital that's higher in energy. There was one electron from this atom, one electron from that atom. After we've drawn the molecular orbitals in the middle, then we put the electrons in the same way we did when we were just filling up atomic orbital diagrams. You put them in the lowest ones first. If there's degenerate orbitals, they'll go in there one at a time and until they have to pair up before they move on to the next energy. So we describe the bond order for diatomic molecules as the number of electrons that are in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals divided by 2. So for hydrogen, that's 2 minus 0 divided by 2. So let's go back and look at that. So the bond order here, number of electrons in bonding orbitals. So this is a bonding orbital that has 2 electrons in it. Subtract the number in anti-bonding orbitals. Well, here's the anti-bonding orbital, doesn't have any electrons in it. So that's 0. And then you divide that by 2. Because there's 2 atoms. And so you end up with a bonding order of 1. If you have a bond order that's positive, the chemical bond will form because that indicates that by forming the bond, the electrons will have lower energy, and that's a favorable thing. The stronger the bond, the higher the bond order. If you have a bond order that's 0 or that's negative, then a bond will not form because there'd be no energy benefit if it was 0, and there would be a decrease. Well, your energy would get higher if the bond order was negative, and so then the bond wouldn't form either. So hopefully as we go on, some of this might become a little clearer. Let's look at He2. So if we do this scheme for He2, here's helium atom and another helium atom. So helium atom has 2 electrons in its 1s orbital. When we combine these 1s orbitals, we can add them to form a bonding orbital and subtract them to form an anti-bonding orbital. This will be higher in energy, this will be lower in energy. For this molecule, we have 1, 2, 3, 4 electrons. So when we put them in, we go 1, 2, 3, 4. So for this one, those two molecular orbitals are both full. And calculate the bond order. It's the number in bonding orbitals, that's these two, minus the number in antibonding orbitals, those two. 2 minus 2 is 0, divided by 2 is still 0. The bond order is 0, which predicts that He2 molecule doesn't form. And it doesn't. Any questions? What if we had an He2 plus ion? I know these are very, very strange things we're looking at here. Well, He2 plus would be like that He2 molecule we were just looking at, except it's short one electron. It's missing an electron, right? So when we looked at the atomic orbitals, we'd have a total of 3 electrons. So 2 over here and 1 over there. Just because we're saying we're looking at He2 plus, so we have to be missing an electron. So there's 3 electrons then. 2 will go into the bonding orbital, and then 1 goes into the antibonding orbital, because that's all the electrons there are. And then we can calculate the bond order. How many electrons in bonding orbitals? 2. How many in antibonding? 1. There's 1 up here. And then divided by 2. So 2 minus 1 is 1 divided by 2, so this is 1/2. Bond order predicts that this exists. It does. It's weird, it's not common. You're not going to run into it in this class anywhere except in this discussion of molecular orbitals, but it does exist. And the test of a theory or a model is, does it match up with experimental observation, right? So it's important that it matches up. So, summary of what we've talked about for molecular orbitals. So we approximate molecular orbitals as linear combinations of atomic orbitals. And you're going to have the same number of molecular orbitals as you had atomic orbitals. When you combine 2 atomic orbitals, you're going to get 1 molecular orbital that's lower in energy and 1 that's higher. The lower is called a bonding, the higher energy one is called an antibonding orbital. When you're assigning electrons to the molecular orbitals, you fill the lowest energy ones first. You follow Hund's rule, where they're going to go in singly first with parallel spins, and then you pair them up with opposite spins. In order to have a stable bond, the bond order has to be positive. That just means that you have more electrons in the bonding orbitals than in the antibonding orbitals, because the antibonding orbitals fight against bonding, and the bonding orbitals promote bonding. Use molecular orbital theory to predict the bond order in H2+. Is that bond stronger or weaker than the H2 bond? So we've got energy going up, and we're going to look at the atomic orbitals for each of these atoms. We've got hydrogen and hydrogen. This is a 1s orbital. Hydrogen has 1 electron, and hydrogen has 1 electron. But if we're looking at H2+, how does it get a positive charge? By losing an electron. So we need to lose one of these electrons. So poof, that one's gone. So this then is a hydrogen ion interacting with a hydrogen atom. So we make the molecular orbitals through the linear combination of these 2 1s orbitals. And so we're going to get 2 molecular orbitals. One's going to be lower in energy, one's going to be higher. So we're going to get 1 down here and 1 up here. This one is called sigma 1s. This one is called sigma star 1s. The star indicates that it's an antibonding orbital. The 1s is just telling us what kind of atomic orbitals were used to form these. So here's my molecular orbitals in the center, and I have one electron to put in. This is really hard, right? Where do I put it? Well, you put it in the lowest orbital, lowest energy orbital, and so there, that's it. So it's asking us to predict the bond order. So the bond order for this will equal the number, I need to know, the number of electrons in bonding orbitals, which is how many? 1. Minus the number of electrons in antibonding orbitals, 0, divided by 2. So bond order is 1/2. So the bond order is 1/2. And then the next question, is this bond stronger or weaker than the H2 bond? Well, let's go back and look at the H2 bond. Here's the H2. What was its bond order? 1. Because here we have 2 electrons in the bonding orbitals and 0 in the antibonding, and divided by 2, and so here the bond order is 1. So compared to H2 with a bond order of 1, this is lower, it's smaller, so this bond is weaker. See how that kind of works? Okay, let's look at, we just looked at period 1, hydrogen and helium. Let's look at period 2 in the periodic table. We're looking at homonuclear diatomic molecules. Homonuclear means the nuclei are the same. So it's two atoms of the same element, and diatomic, it's only 2. So again, we're only looking at valence electrons and valence orbitals. So here we're looking at lithium 2, Li2. So here's a lithium atom. It has 1 valence electron in the 2s orbital, and the other lithium atom has 1 valence electron in the 2s orbital. When 2s orbitals combine, they make orbitals, molecular orbitals, very similar to the 1s, where one's higher and one's lower in energy. We have a bonding and an antibonding. The names are sigma 2s and sigma star 2s. So we take these 2 electrons and we put them into the molecular orbitals, and we've got 2 down here, and that's it. So then when we calculate bond order, we have 2 in the bonding orbitals, none in the antibonding orbitals, then we divide that by 2 and we have a bond order of 1, predicting that this does exist. And it does. In the gas phase, it's unusual, but it does exist. Let's look at Be2, beryllium. So beryllium's got 2 valence electrons. So the 2s and the 2s, and those combined, we've got the same molecular orbitals here, 2 sigma 2s and sigma star 2s. But when we put the 4 electrons in here, we get 2 in the bonding and 2 in the antibonding. And when we calculate the bond order, it's 0, predicting that this doesn't exist, that it's unstable, and that's correct. When we get past beryllium, now we have to think about the p orbitals. So we're going to combine pairs of p orbitals. So if we look at the p orbitals that are along the x-axis in both of these atoms, we can combine them adding or subtracting, constructive or destructive. You add these, you get a bonding orbital that looks kind of like that. And destructive interference gives you something that looks like this. So one's higher in energy, one's lower in energy. If you look down the internuclear axis from one atom's nucleus to the other, it's going to be spherical, circular. So it's a sigma bond. I'm sorry, a sigma orbital. So this one's called sigma 2p because it's made from 2p orbitals, and this is sigma star 2p. Okay? The other p orbitals are perpendicular. So if we take the py orbitals from both atoms and combine those, constructive interference, constructively adding them gives us one of these, and destructive gives us that. These are called pi molecular orbitals because this one is sort of shaped like a sideways pie, right? And then that one's just weird. But this is pi 2p, it's a bonding orbital, and that's pi star 2p. Bless you. There's still two more orbitals, one on each of those atoms, and these are the pz. Each of these atoms has 3 p orbitals, and they're oriented perpendicularly along the x, y, and z axes. So we can take these two and combine them, and we get a bonding and antibonding. And so these are the same shapes as these, but we're looking at it from a different perspective, right? So here we're looking at it, we're trying to look at it three-dimensionally as coming at us, and here we're looking down on top of it. And so here we see even more clearly that that's a pi. It's like a pi bond in valence bond theory. So again, pi 2p and pi star 2p. Then just to make things fun, the relative ordering for those orbitals that we get from the 2p atomic orbitals isn't the same for all the atoms. It's determined using computers. Generally, boron, carbon, and nitrogen have different orders than oxygen, fluorine, and neon. The typical order is that the sigma bonding is lowest in energy, then the pi, then pi star, and sigma star. So this is the expected order. Here we've got our s orbitals forming sigma 2s and sigma star 2s. We talked about that. Here is what we're just learning about now with the p orbitals. When the p orbitals overlap, they can form a sigma bonding and a sigma antibonding. And then the two that are perpendicular to those form pi orbitals, pi 2p and pi star 2p. These are degenerate, these two, because they're the same energy. They're just differently oriented in space. So this is expected or normal. This is weird. So what's different here is just these two. Over here, the sigma is lower, and then the pi is next. Here, the pi is lower, and then the sigma. So that's what's different. How do you remember this? Be careful now. Be careful now. The first three letters here, B for boron, C for carbon, N for nitrogen. So if you're looking at B2, C2, or N2, be careful now. You have to switch that order. So here's showing how the order switches. This is regular, where the sigma is lower and then the pi. And in boron, carbon, and nitrogen, these two switch places. The pi orbitals are the same in energy, but now the sigma is higher than it would be with the oxygen, fluorine, nitrogen, everybody else. And it's because of increased mixing between the s and the p orbitals. So this diagram is showing just the molecular orbitals for 6 different homonuclear diatomic molecules. So here's our be careful now group, boron, carbon, and nitrogen. And we see that the pi bonding and sigma are different in order than they are over here. So boron has 3 valence electrons, right? So we put 3 from each, gives us a total of 6 electrons. So we put them in there like this, 1, 2, 3, 4, 5, 6. And then when we look at the bond order, we're counting how many are in bonding orbitals. Well, there's 2 and 2. So 4 in bonding orbitals. Subtract the number in antibonding orbitals and divide by 2. You get a bond order of 1. Excuse me. For carbon, the molecular orbitals are going to be the same, but now we have 2 more electrons, 1 from each carbon. And so those will fill in this pi, the pi bonding orbitals there. And you can calculate the bond order there. Bond order is 2. In this table, we're also seeing the bond energy and the bond length. And we see that as the bond order increases, the bond energy increases. It's stronger. And the bond length gets shorter because a stronger bond is shorter. And here's nitrogen. Again, adding 2 more electrons compared to C2, and those go in here. So this has a bond order of 3. Its bond energy is higher than for C2, and the bond length is shorter. We go to O2. This has the regular order where the sigma 2p and the pi 2p are in this order as opposed to the be careful now elements. So here we've got 6 electrons from each, and so a total of 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we can calculate the bond order. This is a bond order of 2. And we see, compared to nitrogen, bond order is less, the strength of the bond is less, and the bond is longer. When we go to fluorine, we're adding 2 more electrons. Those are going into pi star antibonding orbitals. And so its bond order is decreasing. We see a decrease in bond strength, increase in bond length. When we get to neon and E2, and calculate the bond order there, it's 0. So we don't have a bond energy or bond length because this doesn't exist. Any questions? So we know from experiment that oxygen is paramagnetic. We talked about paramagnetic and diamagnetic, right? Diamagnetic, di means 2, 2 by 2, like Noah's Ark, all the electrons are paired up. In paramagnetic, which I always think it should mean they're paired up, but it doesn't. Noah's Ark, 2 by 2, paired up, diamagnetic. Paramagnetic, they're not all paired up. And so we have some unpaired electrons, and those are the ones that can interact, be attracted to a magnetic field. So I'm going to show you a demonstration. But before I show that to you, let's look at the Lewis model and the valence bond model. This is the Lewis structure for an oxygen molecule. Do you see any unpaired electrons? Nope. Here is a bonding model from valence bond theory. Do you see any unpaired electrons? These 2 electrons are paired in this pi bond. Again, no unpaired electrons. Both of these models predict that oxygen would be diamagnetic, not interacting with the magnetic field. Okay, so that is liquid We're just going to do liquid oxygen and liquid
So
nitrogen.
we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled door. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. Then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
Liquid nitrogen is crazy cold, and so he's passing the oxygen through that tube. It's like a super duper freezer, and it'll cause gaseous oxygen to condense into a liquid. It's so cold that the tubing's got ice formed all over it. Liquid oxygen. So that's liquid nitrogen. It's a very strong magnet. It just goes straight through. Just, you know, what you would expect. Here's the liquid oxygen. What? It sticks. Isn't that crazy? Because oxygen is paramagnetic. It has unpaired electrons that interact with the magnetic field, and so that liquid oxygen sticks in that magnetic field. The nitrogen doesn't. Nice thing is you don't have to clean any of that up. It just vaporizes and it's gone back into the air. What looks like smoke here is not smoke, and it's not the oxygen vapor. It's the coldness from the liquid oxygen causing water vapor in the air to condense and form that kind of cloud. Any questions? Yeah. That's an excellent question. Can you drink liquid oxygen? No, because it would freeze your mouth instantly. Yeah. So that you couldn't physically do it because it would freeze your mouth. Have you seen any of our science demonstrations where they take the liquid nitrogen and they stick things in it? So there'll be another one in the fall around Halloween. You should make sure to go to it. So, and you can probably find demonstrations shown on YouTube as well of things in liquid nitrogen. It's pretty fun. So you can take like a rose and dip it in liquid nitrogen. And you pull it out and it looks okay, and then you tap it on the counter and it shatters. My physics professor in college did a demonstration that I just really loved. He took a peeled banana and stuck it on a piece of wooden dowel. So it kind of looked like a hammer, but it's a banana. He sticks it in the liquid nitrogen for a little while, gets it good and frozen, uses a banana to hammer a nail into a piece of wood. Rubber ball, throw it in there, get it nice and cold, go to bounce it on the floor, shatters. So liquid nitrogen or liquid oxygen would do that to your mouth, so no, you couldn't. Yeah?
Is this what they stick that food into in the mall? Have like these little like balls and I don't know, maybe this.
Like the dragon and stuff,
Yeah.
and like smoke comes out of your mouth.
I don't know. I haven't seen that.
It's like super frozen.
If it's super frozen, it's probably liquid nitrogen. Yeah. And liquid nitrogen is also what they use to get rid of warts.
Yeah.
And it does so by freezing the wart, which your experience afterward is almost like it's been burned because it damages the tissue in a similar way. But you can freeze warts off your body. Yeah, you can feel it. I mean, it gets numb pretty fast, but then when it warms up again, you feel it and it hurts again. It's not horribly painful, but it's not fun either. It's not something you would want to do for fun. The danger of messing around with liquid nitrogen or liquid oxygen is frostbite. I mean, you can severely damage your skin. You know, if you stuck your finger in there and froze it, you could shatter your finger, right? That's just super gross. But even if you didn't shatter it and just let it thaw out, freezing it like that is going to damage all of the cells and going to be very, very destructive. Yeah, so you got to be careful. And so they make ice cream with liquid nitrogen, and they've been doing all kinds of fun stuff with liquid nitrogen in food. You got to be careful with that. Yeah.
Would we be using that in the ice cream lab?
No, we're not going to play around with liquid nitrogen. Sorry. So we look at these other models, Lewis theory, valence bond theory. This is something that they don't explain, which tells us that they're not the end-all be-all of models. So let's look back here at the oxygen molecular orbital diagram. There are the two unpaired electrons, right? These two unpaired electrons are why the oxygen stuck between the poles of that magnet. Here's nitrogen. No unpaired electrons. The nitrogen went straight through. Fluorine gas, as a liquid, would also be predicted to go straight through. It's not paramagnetic. So let's do another practice one here. Draw a molecular orbital energy diagram and determine the bond order for the N2+ ion. So we look at, to begin with, what are the atomic orbitals that we've got. So nitrogen, we're looking at 2p and 2s. When the s orbitals overlap, we get a sigma 2s and a sigma star 2s. We get the idea. And when the p orbitals overlap, we get sigma and pi, sigma star and pi star. So this is not, no it is, this is, be careful now. This is nitrogen, and so we have to watch the order there. We expect the sigma to be the lowest, but this one is not what we expect, and so the pi bonding is lower in energy than the sigma, and then we've got the pi antibonding and the sigma antibonding. And yeah, my drawing leaves a little bit to be desired, but it's harder than it looks. So this is sigma star 2p, and that's pi star 2p. This is sigma 2p and pi 2p. The good news is, on your exam, I'm going to test you over some of this stuff, but I'm not going to make you draw the diagram. I'll give you a blank diagram, and you have to fill the electrons in, or I'll give you the orbital diagram with all the electrons in and ask you questions about it, but I'm not going to make you draw this, okay? So that's good. So we're looking at N2 plus. So we'll put N over here, and one of these has to be missing an electron. We'll make it this one over here. So a nitrogen atom has 5 valence electrons, and those are 2 of them in the S and 3 in the P. And then over here for the other nitrogen, it's missing 1 electron, so it's got 4 valence electrons. Okay? So I'm going to take those. I've got a total of 9 electrons, right? 5 from one, 4 from the other. And I'm going to fill this middle part in using the same rules that we did to fill in regular atomic orbitals. You go with the lowest energy first. So 1, 2, those are going to pair up before I move up in energy. 3, 4, 5. Now this 6th one is going to go over here and take his own orbital. And 7, this will have to pair up. 8, that'll have to pair up. And then 9 ends up there. So from that, we can answer questions like, do we expect this bond to be stronger or weaker than in the N2 molecule? Well, what's our bond order here? How many in bonding orbitals? 2, 4, 6, 7, right? 7 in bonding orbitals, and how many in antibonding orbitals? 2. Here, what I'm going to do is I'm going to highlight the antibonding orbitals so we can see them a little more clearly. So we have 2, 4, 6, 7 in the bonding orbitals and 2 in the antibonding orbitals. So 7 minus 2 divided by 2, that's going to be 5 halves, or that to be an equal sign, 2.5. What is the bond order for the nitrogen molecule? Well, the nitrogen molecule would have 1 more electron, right? We have 1 more electron in there. So for N2, let's do it over here where I have some more room. For N2, the bond order is going to be 2, 4, 6, 8 minus 2 divided by 2, which is 6 halves, or 3. So by losing that electron, this N2 plus only has a bond order of 2.5. That means it's weaker than N2. Is it diamagnetic or paramagnetic? So let me get rid of the, we're not talking about the nitrogen. I stuck that in there. We're looking at the N2 plus. Are all the electrons paired up? No. So then is that diamagnetic or paramagnetic? Paramagnetic. It's diamagnetic. Di means 2. 2 by 2, Noah's Ark, they're all paired up. This is not, so it's paramagnetic. Those are the sorts of questions that you could expect on an exam. Okay? Second period, heteronuclear diatomic molecules. So here we have 2 different elements. This is nitrogen monoxide. The oxygen is more electronegative, so its atomic orbitals are a little bit lower in energy than the nitrogen. And so that affects the energy levels of the molecular orbitals a little bit. So that's nitrogen monoxide. Here's hydrogen fluoride. So hydrogen atom, just a 1s, and the fluorine atom is using its 2p orbitals. The fluorine atom is so electronegative that its 2p orbitals are lower in energy than hydrogen's 1s orbital. It's really kind of crazy. So these overlap and combine in a very, very strange way. I won't ask you questions about that. That's just weird. What's happening here is that one of the 2p orbitals is overlapping with the hydrogen. It's combining to form a sigma and sigma star. And then these other two are just sitting there. They're not antibonding, they're non-bonding. We're going to skip that one. So a couple more things that molecular orbital theory explains that Lewis and valence bond theory do not. So we talked about resonance, and we looked at the Lewis structure for ozone, and this is the best that Lewis structure can do. Draw both possible structures, a double-headed arrow in between, and we interpret that to mean that the actual structure is between that. It's not a double bond and a single bond, it's like a 1.5 bond for both, but we can't draw that. Valence bond theory doesn't do any better. Here we have a double bond here and a single bond there, and there's no way to do it in between. Experimentally, though, we know that ozone has 2 identical bonds. Neither is double or single, but they are the same. So these 2 models don't work. Molecular orbital theory works. Thankfully, we're not going to look at the diagram for how this works, but hopefully, having looked at those, you can imagine and believe me when I say that this is how it works. So we're forming pi molecular orbitals from the combination of 3 2p orbitals, 1 from each atom, and that's combined over the entire molecule. So that's sort of the half bond, and then there's a regular bond here. Does that make sense? Instead of an orbital that's just localized between 2 atoms, this is an orbital that's delocalized. It's over the entire molecule. And so we can explain some of these resonance structures using molecular orbital theory. One that's very, very important for organic chemistry, which some of you will be taking, is benzene. So benzene is a carbon ring, 6 carbons in a ring, and each of those carbons has a hydrogen bonded to it. And the Lewis model represents this as 2 resonance structures. So here the carbon double bond is between these 2 carbons, and over here that one has a single. So we're just moving the double bonds around, and that's resonance, right? Resonance, that word suggests vibrating back and forth to me, but that's not what happens. It's actually a hybrid, right? It's a combination. It's between these 2. It's neither of them. Molecular orbital theory can explain benzene as a delocalized molecular orbital that goes over the entire molecule. And so this explains a lot of things about benzene that we can't understand otherwise. So benzene is highly symmetrical. It has 6 identical carbon-carbon bonds. And knowing that molecular orbitals like this that are delocalized is possible helps us to say, oh, okay. So that's what we're going for with the molecular orbital theory presentation to you, is that you understand just enough of it that when I tell you that this is a delocalized molecular orbital, you say, oh, okay, I could buy that. Do you want me to explain all the details? No, you don't. And honestly, I couldn't, because I've forgotten. I only remember what I need to remember, right? Any questions?